Nice. Okay, so now let's talk about insertion sort. We will try to approach linked lists by we will approach it by from insertion sort as a motivation. So now insertion sort, so there is a stream of data that is coming in. Let's say, right now you know how to read data from files also. Let's say there is a huge file present on the disk and you are reading in data from the disk, and then the data stream is like this. So this is 2, 3, -1, 10, 30, 40, 8, 7, etc. So, so there are two challenges here, okay, and we want to, as we read the data, we want to keep the data in a sorted order. So one way of doing it is you read, let's say you are reading it from left to right, you read 2 and then and then the next element that you read is 3. So 3 is greater than 2, so the list is already in sorted order. And now when you read -1, when we read -1, so what happens? -1, you compare -1 with 3, -1 is less than 3. So you move forward and you compare -1 with 2, and -1 is less than 2. So you put -1 here. If you are using an array to store this data, naturally you can see, so the way we do it is 2, 3 is present. And in order to, when we compare -1 with 3, so what do we do? So 3 is greater than -1. So you move 3 to this position, and then so you have -1 here. You don't need to actually put it there. And then you compare -1 with 2, and -1 is less than 2. So you move -1 here, 2, 3. So now you read 10, you compare 10 with 3, so no problem. So you will start from here. So the list will look like this. So -1, 2, 3, 10. And then when we read 30 and then 40 also, no, we are doing good. No problem. -1, 2, 3, 10, 30, and then 40 also is the same. So -1, 2, 3, 10, 30, 40. And then when we read 8, so you compare, this is when the challenge comes. So first of all, there should be more space for elements. So now when you compare 8 with 40, you compare 8 with 30, 10, and you keep moving elements, and before 10, you insert it. So how many copy operations will be there when we insert 8 here? When we insert 8 into the list, how many copy operations are involved? So 10, 30, 40 needs to be moved one position to the right. So 3 copy operations are present. So this is how insertion sort works, and needless to say, this is a very expensive algorithm. What is the worst case for this one? What is the worst case? When will this algorithm perform terrible? When we insert elements in the descending order. Yeah. So let's see here. So if the elements are inserted in, let's say the elements are 90, 80, 70, 60, 50, 40, 30, 20, 10. So when the elements are in descending order, or let's say the elements are, you insert the elements n, n minus 1, n minus 2, so on. These are the n elements you are inserting. So how many, so you can easily insert n, so one operation. And when you are inserting n minus 1, how many copy operations? There is no, let's say we are just counting copy operation. So for inserting n, there are no copy operations. For when you are inserting n minus 1, how many copy operations? Inserting n minus 2, 2 copy operations. So on, if you extend this logic, then you will have, while inserting 1, we require n minus 1 copy operations. And the total number of comparisons is n minus 1 into n plus 1 by 2. So this is approximately n square. Okay, it's a quadratic time algorithm. So this is about insertion sort. The challenge, of course, with insertion sort is, apart from this, is if you don't know how many elements you are going to read, then what should be the size of the array that you have to allocate? You don't have an idea, right? Whether, if you don't know whether you are doing insertion sort using an array, and if you don't know the number of elements that you would like to insert, then the problem is what will be the size of the array? Whether the size of the array is 100, 200, 300, what is it? We are not sure. So that's going to be a problem. You're all with me so far? One is the bad time complexity. The second is the memory allocation. So at least one good thing about insertion sort is, at any point, if you want to search what element is present, then you can do a binary search. You can do, because the list is all the time sorted, right? At any point in time, the array that we are maintaining so far, it is sorted, so we can do binary search, because binary search requires that the elements are in a sorted order. All right. Okay, so now at least one problem we can solve using linked lists is, if you declare the array in as a global array, where will the memory for a global array allocated? Array as a global variable, if you declare array as a global variable, it will be allocated memory in the data section. What is the lifetime of the array? The whole program execution time. Excellent. You're all with me. Awesome. So now, but we want to solve this problem that we should be able to handle data. We don't know the size of the data. Okay. So one approach is, of course, you use malloc and realloc. Initially, you think initially you allocate memory for, let's say, some 100 elements, and later on, when you figure out that you require more memory, you can do a realloc for 125 elements. And later on, if the data size, when the data size is greater than 100, yes, greater than 100. So similarly, once you figure out the data size is greater than 125, you do one more realloc. But these reallocs are expensive. Okay, remember, this realloc is expensive. I'm just kind of reviewing these ideas. So what we want to do instead, this is the place where we introduce a linked list. So initially our list is empty. So we will have a list header. Let's say there is one variable list header. So this is, so this list header, it contains, initially when we see an element 10, we store, let's go back and look at the original list of elements that we have. Let's go back. Okay. So now let me erase some of this. So this is all initially we worked with arrays. Now we want to solve this problem using linked lists. Great. So what do we do? So initially we have we create an element with which contains 2. And then after you see element 3, you allocate one more node. So you allocate memory for 2. So the type of the structure, you can have something like struct node is something like this. Okay, int whatever. Let's say the 2 3 minus 1. What do we call that field? I don't want to call it as marks because there is -1 there. It's depressing. So it cannot be age. Usual things are ruled out. Int num, it's some score, negative score. Okay, some num. Okay. And then you so struct node star next. Hey, can someone have a negative height, man? Bank balance, negative bank balance. Temperature, yeah, temperature may be good. Yeah, moral alternative. No. Okay, enough. So yeah, so struct node. So this is the type of the node. It looks like it has 2 fields. One is the place, where let's say it is number of friends or all whatever. Yeah, IQ, negative IQ. See, minus is the temperature is the closest, which doesn't hurt anyone's sentiments badly. So struct node star next. Okay, so the second one is a pointer. So now when we see 3, so we create a new node, and no, this is always points to null. Okay, this is let's say I use this notation for null. So now when we look at -1, so what we do is now if you are trying to do an insertion sort, -1 should be present at the beginning. So we create -1 and we create a link to this -1 and put it here. Okay. So when we do linkers, if you see, when we are trying to inserting -1 is pretty simple when we are using linker lists. And then when we want to insert 10, null is not /0. Null is actually equal to 0. I think /0 is also 0, I guess. Yeah. So and then when we want to insert 30, so you keep, now this is 10, right? So you are inserting 10 and you get 10 here, and this is, now this is no longer null. So now this contains the pointer for this. Are you getting a logical picture? Let me use capital N for null, okay, to make it easy. So are you getting a picture of what is going on? Logically, we have to write the code. Now, when we want to insert 30, you start from here, you keep going forward, and then finally you put 30 here, and this goes, and null will be present. And now again, when we are inserting 40, so we start from -1, 2, compare it against 3, 10, 30, and then 40, you will have 40. So now comes the fun part. Actually, this is where the challenge lies. Now, when you want to insert 8, so you compare with -1 and you compare with 2, you compare with 3. So 8 is, so 3 is less than 8. You compare 8 with 10 and 8 is less than 10. So the position of the node 8, this is the node 8 that you create. The position of node 8 is in between 3 and 10. So what we do is, you take this, you destroy this link, you take this link and then you make it this point to this, and you take this one and you make it point to this. Are you with me here? Logically, are you all with me here? So now this also begs an interesting question. And then of course, when you want to insert 7, so you have to insert 7 between 3 and 8. So what do we do? So you compare -1 with 7. Let's say this is 7. And let me use a different color so that it becomes easy for you. So this link we destroy and we make this point to 7, and 7 will point to 8, and the linked list remains the same. Okay, so this is the high level picture. So in the exam, there is one question: can you do binary search using on linked list? Can you do binary search on linked list? You cannot do binary search on linked list because you don't know the address of the middle element. If it is an array, if this is an array, and if you know the base address of the array, this is the base address. If you know the base address of the array, you can directly go and check the middle element. But in the case of binary search, you cannot go, you don't have handle of the middle element because each of these nodes are scattered around in the heap. Okay, one answer from the exam answered that you cannot. Did I ask this question in the exam? How many of you got it right? How many of you got it wrong? It's okay, no shame, but those of you who got it wrong, do you now understand why you are wrong? Okay. So if I ask you, okay, what is the address of node which contains 30? You have to traverse the linked list and go there. You cannot. So if you have a linked list, if I ask you, can you get me the ith element in the linked list? You have to traverse the linked list. You cannot go and access the ith element in the linked list directly. But if it is an array, if I ask you, can you give me the ith element in the linked list? In the array, you can directly say A of I. Okay, so Abhinav has it. So if you are accessing ith element, you have to chase the pointer I times. This is the 0th element, or no, this is the first element, this is the second element, this is the third, this is fourth, fifth. In order to access the first element, you have to chase the pointer once. In order to access the second element, you have to chase these pointers twice. And in order to access the third element, which is 7, actually, sorry, the third element is 7. In order to access the third element 7, you have to chase the pointer thrice. You cannot do binary search. Binary search doesn't make sense because you cannot do random access. But in the case of an array, if I ask you to find the ith element, you can directly go and access the ith element. It's okay. One here and there, it's all how do we count, but it's not going to have a big impact. Are you with me here? Okay. So now if you understood this, then let's try to write code for this. You have to help me out. Okay, I completely didn't prepare. I just came straight. So let's see, you help me out here in writing the code. There are 166 students only. Other 100 students, they are all, they don't know what they are doing. how to read it. You will see now insertion sort.c using linked list. Okay, let's code together. You help me out. stdio.h. What are the functions we have to support? So we would like to support an insert. First, we need to have a. So we have to define. So we have to define the structure of the node. So we create a new type. How do we create a new type? We have to use type def. Okay, we have to use type def. Type def struct node. So and then we use capital node. So we are creating a new type called as node, capital node. Are you with me here? We are creating a new data type called as node, capital node, NODE. Yash has an interesting question. Can we store all addresses of the list in a separate array? Then we can access the middle element for binary search. Good idea. Very good idea. Yes. But that's not a linked list, but it's an approach to solve some interesting problems. You can reduce the amount of data copy using that. It's a good question. Okay. Well, it's not exactly same as array of structures, but anyway, let's focus on this problem. Okay, let's. Hey, yeah, Ishwar has this point. We face the same realloc problem then too. Yes, thank you, Ishwar. Yeah. So what are the fields that we would like to have? We would like to have, why all the time marks? Int temperature. Or we'll have int cool, how cool someone. How many, if you don't know the number of records, yes, then what should be the size of the array which holds the addresses? keep okay, we will see. We'll keep it ambiguous and interesting. Okay, so now, hey, here comes the interesting part. I want you to pay attention. Here we want to define a variable called as next. And this next is a pointer. This next contains the address of an object, and the type of, there are two equivalent types in this story. In the way we are defining things, we are defining two equivalent types at the same time. Two equivalent types. What is that? What are the two equivalent types? One is a struct node. This is equivalent to struct node. Please pay attention. So struct node is equivalent to node. So both. So when we say some memory, the type of some variable is a struct node, it is same as telling that the type of that variable is a capital node. Are you with me? So now what we want to do is we will say struct node here next. So next contains the address of a object. Next contains the address of an object. And what is the type of that object? What is the type of that object? The type of that object is capital node or struct node, small node. Okay, so next contains an address, and the next contains the address to a object, and the type of that object is struct node or capital. So this is this when we are working with linked lists, or when you are working with tree data structures, when you are working with any kind of data structures, the first thing we have to figure out is what is the what are the fields within that the structure that we are working with. Are you all with me? Some of you told me in the feedback form you have trouble with structures. So there is this interesting question. Why don't we write node star next? This doesn't work because compiler didn't still see this node definition. Compiler didn't see this node definition yet. So because of that, line number 7 doesn't go. Well, there are ways to handle it if compiler really wants to do it. So, but there are some historical reasons. But I think when C compiler is designed for the first time, long time back, this is the reason that when we are declaring node, when we use node on line number 7, it's not yet defined. That why am I getting signed out? Hey, can you hear me now? There is some problem. I got signed out. Okay, I'm sorry. For some reason, I'm getting automatically signed out today saying that I'm signed in somewhere else, but it's not really the case. Okay. Oh, is it? Good. Yeah. So, yeah, how about this now? So you're all with me here so far in the story? Okay, good. Yeah. So now, yeah, so now what are the functions that we need? We should have a insert. Yeah, before that, we need to have, once we have this, we need to have a list header which holds the address of the first element in the list. Does it make sense? We need to hold the address of the first element in the list. Otherwise, how do we traverse this linked list? We cannot, right? And then, in fact, it could be initialized to null to start with, because it's when we start, there is no list at all. So we can initialize it to null pointer. List header or head, or maybe for the sake of, yeah, I can just use head. So the functions that we would like to define: insert node. Before even insert node, let's say there is an insert node. Yeah. So now we would like to add two functions. One function is allocate node. So here, what do we do? So we just do return. What should we write here? Return. What should we are here in this function, we allocate memory for in node. What should we do here? Return, we have to do allocate first. malloc size of what? Size of node. Okay. See, right now, this looks like a very why can't we just use malloc wherever we are doing? But let's say down the lane, you can have something like char star name, then you and to passing to allocate node. And what we can do is we can create a node and we can create memory for a string pointed to by name. And we can do a bunch of other things also in this function later on if the program becomes more complex. But for the time being, we are not doing any of that. Yeah, we will hold it. Okay, we'll take it up later. Okay, let's first understand this. What I'm trying to tell is right now it looks like a allocate node looks like a overkill, but you will see programming scenarios where this is not really an overkill. Okay, how many of you think on the face of it it's a overkill? Because it looks like an overkill because we are not doing anything. We are just doing an malloc on line 14. So why can't we, instead of calling allocate node, why can't we just do an malloc there itself? Okay, but it has its advantages when you are working with more complex structures. Yeah, of course, functions are always better for program organization. Are you fine with the allocate node function? Are you all with me here? Yes, no? Happy? Good. So now what we do is we will do free node. It takes as parameter free node star node. And then here we just do free node. That's it. Okay, free node. So allocate node, free node. This will, the function 12 of allocate node and free node, when we step up the game, they will really come in handy. That's all I'm trying to say here. And then there is an insert node function. Insert node, node star node. This is what we want to do. I don't want to use here. Make it too many nodes. So make it plural. Where should I make it plural? So Vaibhav has a point, but we will insert a node. We write code to figure out where to insert it. Okay. And then void delete node, node star. So actually void, yeah. Okay, we will see. Okay, so we are all good here. So let's try to write the search node function. Search node function is the easiest. So let's try to write the search node function. Can you tell me how to write the search node function? So we start with C node is equal to head. Okay. And then what do we do? And we check if C node is not equal to null. Because if the, let's say if there is no element in the list, what will head be? If there is no element in the list, what will head be? Head contain. Remember, head is initialized to null here. Okay. And then what do? We come down here and we check. So what do we check? If C node cool. Okay, yeah, let me use key. If C node key is equal to key, then what do? Then we return C node. Are you with me here on line number? Do you get the if statement so far? And what is the last line here? Or rather here, we can have C node is equal to C node next. We changed it, Bhargav. And then finally, if there is no success, finally, we return null. Are you all with me here? What is happening? So we take the key and we search for the key. And if it is found, then we return that address. Otherwise, we return null. Line number 35, in order to access a element of the list, when we have the address of that structure, then we use the arrow operator. Everyone with me here so far? Happy and happy? All right. I know there are 100 students, 164 students. I hope, I really wish that all of you are with me so far. Okay. So delete node, let's try to do delete node also. Let's try to change the signature of the delete node. So delete node, we just give a key as input and we try to find the node which contains that key and we delete that node. Okay. So shall we do that? So let's, when we do, yeah, so one problem, yeah, this is a very interesting question. So let's say you want to delete you have, this is the linked list that we have, and this is the thing that we want to delete. Okay. If you want to delete this one, what do we need? So we need to create a new link from here to here. Yes or no? This is what we need to do. And then we have to free this one. But the problem is when you do search node, you get the address of this node, but we don't get the address of the previous node. We need to know the address of the previous node. So because of that, we cannot just call search node. Okay, we need to keep track of the previous node also. Okay, we need to keep track of. So later on, you will study in your data structures course. It's not really a big deal. No, we can maintain what are called as doubly linked list, where you keep a pointer to your successor and follower. If you keep a successor to your, if you keep a pointer to your successor and follower, then you can just call search node, and using the search node, you can find the address of the previous node, and we can do the manipulation. Okay, if it's a doubly linked list, you can just use search node. Then the node will have three elements. It will have a next link and a previous link. If you have a next link and a previous link, which is called as a doubly linked list, then why there are dots, double dots, and some things are coming from different people? Is there anything going on? Some Morse code stuff? Okay, so you all with me here now. You understood the idea of doubly linked list and why deleting a node here. But let's say I want you to understand one thing. Let's say this is if Prev is a, yeah, let's go ahead and do it. Okay, let's try. So now what we want to do is we want to continue this thing. Okay, so we copy this. See, we are writing code without compiling it even once. So I don't know what will happen. Yeah, so tell me, help me out here. So yeah, so one thing we need to do. So this is the place where we want to delete. And so we want to do two things. Previous node is equal to C node, and C node is equal to, let's try to do one thing. We will try to take this whole code out so that it becomes, it's possible, Bob, what you mentioned, it is possible. Oh. Why is this happening today? Oh, you can hear me? Okay, good, good. Okay, so now let's, yeah, so delete node, help me out here. So, yes, I wrote code for linked list probably a decade back, maybe. So, yeah, let's see. Prev node is equal to C node and C node is equal to next. So we are using two. So we are using two fingers. One finger keeps track of the previous node. And okay. What is the right way to go about this? Let's try to do this one. If C node is equal to, then previous node is equal to, let me get this one right. What should we write here? Previous node next is equal to, let's say this is the one we are trying to do. This is previous node and this is C node. So previous node next is equal to, no, not C node next, because that's what we want to remove. Are you all with me on this one at least? So what is the invariant that we have? C node holds the pointer to the current node and prev node holds the pointer to the previous node. So if we want to make this next point to the next of the C node. Are you all with me? Make sense? Okay, because where is this? Yeah, this is previous node. This is C node. So previous node. So this blue link is equal to previous node next is equal to C node next. This is how we are setting up this blue link. This is the blue link. Are you with me? This assignment statement is the same, is equivalent to the pictorial equivalent, no, whatever this is the code equivalent for this picture, right? We have to fix some things. We have to fix some few things, but at least in the case of inductive case, now let's say if you are in the middle of something, if you set up things right, then can we say that this code that we have written is equivalent to the blue arrow that we are setting up here? And after that, we want to release the memory associated with the C node. Yes, no? Okay. And when we are going to when we are iterating back, the current node will move by one step forward, and the previous node the current node becomes the previous node, and and then the next node becomes the current node. That's what we are doing on line 37. Does it make sense? That the current node becomes the previous node, and the next of the current node becomes the current node. No, we have to set up things for the time being. So let's say for the time being, previous node, if it is equal to null, what happens? We will get into trouble. Yeah. So take a look at this code. I want you to take a look at this code and try to fix this code. Can you try to fix this code for me? Someone once wrote something nice. If head is equal to null, return nice. Vansh has a nice thing. Okay. I would say this something like this. If it is the beginning, then previous node will be equal to null, right? Yes or no? If it is the first, if the hit is the first, key is found in the first node of the list. Then what happens if key is found in the first node of the list? Then previous node is equal to null. Okay. So what we do is head is equal to C node next, and free node C node return. Does this make sense now? When will previous node be equal to null? So what happens is, if it is equal to null, we handle it in a different way. That is, if the first element is the key. So then the head, when we release the first, then the head changes, right? Head should point to the next element. And that's what we are doing on line number 35. And then we are freeing the head. Okay. Are you all with me here? What is happening? This is the case. There are two cases here. So there are two cases I would like to consider you. This is case 1. This is case 1. And yeah, this is case 2. Are you all fine with this one? Case 1 and case 2. Case 1 is when it is at the beginning, first element. Case 2 is the node is somewhere in the middle. Let's say if the current node is the last element, then what will happen? So if current node is the last element, then it's not, then you don't need to do anything actually, because if current node, this is the one, if we would like to delete this element from the list, we would like to delete this element from the list. What do we do? So this should point to null. But this null is anyway present here. So when we do prev node of next is equal to C node of next, then automatically null will be set here. So we don't need to do anything special. All good, right? Are you all with me? Everyone? Happy, unhappy? Okay. I would like you to look at this code again later. Okay. So now we have to do insert code, insert. So insertion also, we have to, how do we insert? So let's say, let's do this picture, clear this diagram. So what do we need? You help me out here again. So you came up with cool ideas. So let's say you want to add so here and here you break this one. Okay. So let's say, so this is the new node. Let's call this as node. So this is a new node. So what do we do? So this is P node. This is C node. So what do we do? What is the code that we write to do the insertion? P node of next is equal to, so approximately speaking, so what we do is P node of next is equal to what? This is the logic you need to have in mind. What is P node of next? Equal to, so let's say I will put a int key here so that it is easy for us to do it. What is P node of next is equal to new node. Okay. And what is the next step? What is the next step? New node of next is equal to C node. That's all, no? Only these two statements are good. These two statements are equivalent to the two blue arrows that we are seeing there. Now, shall we write the code and do it? Do you want to write the code for yourselves and try it out, or if I post this today, or you want me to finish it 3:15 time? So you have 3:30, there is a TA session. Would you like to try to write insert node by yourselves? Try it out, it will be nice. Just copy paste it and you do know auto doc, because if I have to send it by email, I know I will take forever. Not at the end, so you need to write code here in the main to read numbers and and then call insert function. You can create even a terminal like we have created some time back for insert, search, and delete and all. Yeah, I know I should create a GitHub repo. Okay, then I'll send it by email. Okay, are you fine with giving it a try? Is it okay? Because I would like you to try, then only you will learn. If you try it out and do it, then that's it. You are done. You know how to do linked list. This is like a homework problem, small homework problem for you. Okay. I will post a form tonight asking how many of you, if you are able to do it, please put it up. Okay. So I would like you to try it out today by tonight, and just let me know whether you are able to do it or not. I want you to insert it in such a way so that the element is the list is sorted all the time. Okay. Do insertion so that the list is sorted. So that way you are doing insertion sort of problem also the same time in a single shot. Okay then. So I will stop here because tomorrow I will take up this program. I would like one of you to share your code by tonight to me, and and then what do I do? And then tomorrow we will take this one and write it into a multi-file program. Okay. Okay, I will send the recording. Sure, I'll do it now itself for a change.